actually doing certain things, right? So this is how we describe certain functions for computers to perform that will hopefully be helpful in some way. Now, I know that that's all a relatively general introduction, but I guess this is really just to say that these are some of the most foundational concepts for quantum computing, which is why we are covering them in the first week. So as always, I will hopefully always try to remember to say this, but we will have question periods sort of throughout the lab session. If you are watching one of the problems I'm working through and you don't understand something, please feel free to hold on to your question until those question periods. We will open up the chat and then I will take some of the questions and answer them live. All right. Quick overview of what we'll be doing today. It's a little bit different just because, again, this is the first lab. There's kind of some administrative stuff we have to do right at the beginning. For those of you who joined later, we also started 5 minutes late, which probably will not be the case going forward. Just wanted to make sure everyone had the chance to get their technology working and get set up properly. So today, first of all, I'll give a brief introduction to myself, who I am, and the background I'm coming from. Like I said, we have a couple of course announcements that we'll be going over here. Next up, we'll just do a couple minutes talking about ground rules for, in a lot of ways, the course, but there's also some specific things in there about how we'll conduct lab sessions. And then these last 3 points here are sort of the main content for our lab today. We'll start things off with a pre-lab feedback, which for this week is just going to be on Zoom. It'll be a ranking preference form where you say how well you understood the content. That's just so that I can gauge what level we're all at and sort of tailor how fast and how much content I go through today. Then we'll do the lab content itself. And then finally, we'll have an identical feedback form right at the very end to gauge, hopefully your understanding of the content has improved over the course of the lab. And we just want to understand exactly how that works. All right, first up, a little bit about me. So as I mentioned at the beginning, my name is Corbin. I am originally from a city in Canada called Calgary, which is kind of known as the cowtown of Canada. I absolutely do own many cowboy hats and ugly plaid shirts and a bunch of other stuff, but luckily we don't wear them all the time, as you can plainly tell right now. I got my introduction to quantum computing in high school as well, actually, which is a little bit rare, but I attended a summer camp at the Institute for Quantum Computing at Waterloo. It was called the Quantum Cryptography School for Young Students, which has always been a bit of a tongue twister. But yeah, I attended that back when I was in grade 10. Absolutely loved it. It's a very high intensity introduction to quantum computing and the math behind it. And ever since then, really, I've felt that quantum computing should be taught way earlier than graduate school. Because for the most part, quantum computing courses don't show up until grad school, which I think is kind of insane. So that's part of why I'm really happy to be here bringing all this content to you in a to a much wider audience as well. As I mentioned, I go to the university, or actually I didn't mention this. I am an undergrad at the University of Waterloo. I'm in my final year of software engineering, which is not the traditional sort of physics background of quantum computing, but I guess just goes to show, if you were there for the TA panel as well on Saturday, I talked a little bit about this, but quantum computing is a very interdisciplinary subject. Therefore, quantum engineers come from a huge variety of backgrounds. I happen to be one of the ones who has come from more of a computer science background. My current quantum computing related work is doing research at a company, or I guess a lab called Qubit, which is a partnership between Harvard and MIT's quantum computing groups. The sort of bite-sized description of what I do there is quantum compilation or circuit compilation. We will get to that later on in the course to give you sort of some sense of what that means, but if you're curious, you can look those things up. And finally, just some fun facts about me. I really, really love these two games. I think they're awesome. And I have some very strange affinity for garlic bread that I have never been able to quite explain. Okay, so now you know a little bit about me. Let's talk a little bit about the course. As was mentioned before, attendance will not be taken in lab this week. In future weeks, we will use Canvas to take attendance. So this week you get a bye, and then even after this week, there are 2 more unexcused absences each semester. As I mentioned, instead of using Canvas to do attendance and polling at the beginning, we're just going to use Zoom polls for today. Homework, a reminder that you won't submit this week's homework until next week, again, when Canvas is available. You might be noticing a trend here where a lot of things are waiting on Canvas. Students should still do the assignment though, because there will be another assignment next week. And the idea is sort of that you work through these 1 week at a time. Both of those assignments will be due on Canvas on Saturday, October 31st at 11:59 p.m. Eastern. Third thing on this slide is Discord. So if you're not already on Discord, definitely make sure you're on there. It's one of the main communication channels we're using to run this course. In particular, the course announcements channel will be where all important course information is logged. So make sure you're keeping an eye on that. Now for some ground rules around how these labs, and like I said, the course in general runs. Probably the number one thing to keep in mind throughout this whole experience is that we as a teaching staff really want to ensure that every student participating in the lab and in the course feels welcomed and included. Hopefully you see this as an important and recurring theme throughout, but we really want to make sure that everybody here has an equal chance to learn. And a lot of times part of learning is being unsure of what's going on and asking questions and getting support. So I really want to personally encourage people to be open with the questions they're asking, and certainly be open on Piazza and other platforms as well. Some things that we ask you not to do. So number one, do not spam the chat or Q&A with repeated questions or messages. For right now, we've just turned off the chat function until we get to the question periods, but just post your question once. I will see it. There's no need to repeatedly copy and paste something. Second, we're not going to have any of this week, but in the future, I might get you to work through some problems on your own in sort of like break sessions during the lab. And we just ask that you don't put answers to the problems in the chat or the Q&A unless I ask you to, just so that everybody has a chance to work through those problems themselves. Fourth point is to keep your questions relevant to the topics being discussed. So I'll pause here just to sort of say, this is, as you can probably tell, a fairly large online course. And I can tell you that the teaching staff behind it is relatively small. And so our primary focus throughout this course is going to be on making sure that everyone is able to learn the content as best as they can. And so that means we are often going to try and address the most relevant, pressing questions about the content being taught, rather than things that are too off topic. We do have Piazza for other content related questions and Discord for questions on logistics. So I just ask that during lab sessions, you try and keep questions relevant to what problems we're actually solving in the lab itself. And then final point here, only raise your hand if the TA asks you to. I haven't planned on using the raise hand feature so far. Maybe that'll change. But yeah, basically, I won't see it if you click raise hands on Zoom or anything like that. Instead, just wait for the question and answer period, and then we'll get to your questions then. So a kind of like a motto, I guess, that we have at Qubit by Qubit is step up and step back. So this is really referring to two types of people, very, very generally. If you are the type of person who is always confident to ask questions and always raises your voice to speak out when you're feeling confused, we ask you to think about stepping back in some circumstances. And all we mean by this is recognizing that there's a lot of students in this course, there's a lot of students in this lab, and everyone deserves the chance to have their own voices be heard. So if you are someone who tends to, be very outgoing, that's awesome. Try to hold on to that enthusiasm, but just be mindful of other people who might be a bit more shy and give them some space to talk as well. Conversely, if you are somebody who tends to find yourself being very shy and not speaking up very often, our ask to you is that you try and step up and be a little bit more forthcoming with your questions and your confusion. Again, a lot of the content in this course is going to be challenging. We make no secret about that, but we really want to be here to support you and make sure you understand it as best you can throughout the course of the term. I believe this is the final point, which kind of relates to what I talked to before, but we will not be able to address all content questions in lecture or in lab. And so basically, if we're not able to answer your question in lectures or in the lab, kind of like the default overflow for other questions that are related to course content in some way is Piazza or Discord. So I know Piazza is being watched by TAs all the time. Make sure to post your question in the relevant folder on Piazza. A lot of us as TAs, when we're going through it, we just automatically filter by whatever week we're looking for. So make sure you use that categorization feature. And finally, is just sort of a general note, we will continue to explore new content each week. And so there is a high chance that a lot of your questions will be answered in due time. So I'll try to point this out when possible and just say really quickly, like, oh, I saw a question from this person. We will get to that in a future week, and just leave it there. But if not, just know that a lot of related content, especially if it has to do with quantum computing, is probably going to be covered later on in the course. Okay, so that is the end of all of our administrative items. We're going to dive into the lab content now. Just before we do that, though, we're going to have a quick pre-lab student feedback form. So we're just going to put up a Zoom poll right now with a simple 1 to 5 rating. And if you could just give this a rating based on your understanding of this week's lecture content, from a scale of 1, where you did not understand anything, all the way up to 5, where you found the content pretty easy or you just already knew it. And this week has been pretty straightforward to you. So I'm just going to give, I don't know, however long it takes for most people to cast their vote. All right, I think we'll close it off there. Okay, so it looks like people, generally speaking, have a good understanding of this week's content, which is good. So I think I'll take sort of a moderate pace as we go through the lab content this week. I guess one final, I promise, administrative note is that starting next week, this little poll thing will be done on Canvas, and that will be how we take attendance for the lab. Okay, so let's talk a little bit about what we're going to do in today's lab session. First of all, we're going to get started with some exercises on binary numbers. I'll talk a little bit more about why this is important for both classical and quantum computing when we get into that section. We'll cover binary to decimal conversions, decimal to binary conversions, as well as how to carry out binary addition by hand. The second major topic is going to be on logic gates. And so logic gates are sort of the next level up from binary. We start talking about operations that you do on binary numbers and how they can be strung into more complicated operations. So the first topic there will be to review some of the standard logic gates that we're going to use to design circuits going forward. And then if we have time, everything thereafter is optional content. So we might have time to go over the design of a 1-bit adder. And then lastly, we might have time to do a very, very brief introduction to algorithms and complexity. This will be covered in much more detail later on. But if we get there, we'll do a really quick introduction to that particular topic. So let's get started with a quick review of binary. And in order to discuss binary numbers, I'm actually going to start with decimal numbers. So whenever you see just a standard number like this, say 147, this is really a shorthand. You have to think of it as a shorthand. What this really represents in full is the following. We take, starting from the right of the number, we take the first digit and multiply it by a power of 10, to the 0 in this case. The second digit is multiplied by the next power of 10, third digit by the next power of 10. Now, if I go ahead and work out all of these numbers, we get 7, 40, and 100. And then if I go ahead and add all of these together, sure enough, I get 147 out the other end. Now, this might seem like a lot of work to go through just to write the number 147, but in reality, this is what's represented every time you write any number ever, right? So every time you write numbers in math class, this is what's really represented. And we call these decimals, or equivalently, you might hear people call them base 10 numbers. And the reason they're called base 10 is because of the number in this column right here. Notice how everything that we're doing is being multiplied by a power of 10. Now, there's no particular reason why this number should be a 10. I've always thought it was just because humans had 10 fingers. I guess there's some controversy around that, but the bottom line is there's no reason this has to be 10. And in fact, for computers clearly don't have 10 fingers. Instead, what computers have is these arrays of switches. And these switches can be either on or off, just like this. And your computer will have tons and tons of these switches, and this is how it remembers things, this is how it does operations, and so on. So you might guess by thinking about switches, since they only have two possibilities, that perhaps computers would work better with a base 2 system, which is equivalently known as binary. So binary works pretty much the same way as decimal. The only difference is, again, this column right here. So I'm going to follow the exact same process I just did for the decimal number. Starting from the right-hand side of the number, I'm going to take the digit and multiply it, not by a power of 10, but this time by a power of 2. Repeat for the next digit over, we get 1 times 2 to the 1, 2 to the 2. And the exponent here, it just goes up by 1 every single time. Might run out of space here. 5, 0 times 2 to the 6, and 1 times 2 to the 7. Okay, I'm going to work these out just fairly quickly. So we get 1, 2, 4, 8, 0, 0, 0, 128. And don't worry if you didn't follow all of that. We're going to do another example in just a second. But my main point here is to just sort of draw a parallel to how we did things in the decimal world. We just multiply through all of these numbers. The final step then is to add them all up. And if you do this addition, you should actually get 147 as your answer. And so this is how we represent things in base 2 instead of base 10. So talking about binary to decimal conversion, I basically already just did an example, but I'll do another one just a little bit, well, I guess just for practice. I'm just going to come up with some arbitrary number here like this, and then we'll do the exact same process once again. Starting from the right-hand side of the number, I take the first digit and I multiply it by the first power of 2. Second digit by the second power of 2, third digit, and so on. Oops, that should be a 2, power of 2. And so hopefully you can follow along with what I'm doing here. This is just a bit of procedure. Okay, and once we get here to the end of our number, we're going to just work out all of these values. Now, I will point out one little trick here, I guess. If you are having difficulty sort of computing these powers of 2 in your head, especially when we get to larger powers of 2, sometimes what I like to do is, as a first step, I will keep the multiplication here and just write down what the power of 2 turns into. So here I would do 1 times 1. This one is 0 times 2, 1 times 4, 1 times, oh, I skipped the number here. Sorry, all of these exponents should just increase by 1 every time. So from 2, we go to 3, 4, and 5. I get 1 times 8, 1 times 16, sorry, 0 times 16, and 1 times 32. Now, you can notice here that all of the numbers, all of the powers of 2 are just doubling each time. So if you have any trouble remembering these anytime, just start at 1 and keep doubling as you go up. And then finally, everything that's multiplied by 0, of course, just turns into a 0. And then we can go ahead and add this thing up. And I believe we get 1243, probably. No, 45. My bad. This should be this should be pretty straightforward. This is like the easiest part of the conversion. All right, so if that's how we do binary to decimal conversion, how do we then do decimal to binary conversion? I'm going to take a just a random number here. Let's say, I don't know, 167. Just write it a little bit further up here. So there are a number of different ways to do decimal to binary conversion. The way that I like to do it is I will start off by writing all the powers of 2. So we'll start off with 1, and then just like I alluded to before, just double it each time, keep doubling. So we start with 1, double it is 2, double that is 4, double that is 8, double that, 16, and so on. You just keep writing these by multiplying the previous number by 2. 32, 64, starting to get a little bit larger here, and 256. Now, once I hit 256, I have exceeded the value I actually want to convert. So I stop, cross out that number, and I go to the next number before it, 128. And then I subtract 128 from my original value. So I'll have a carry here. And I get 39 out of that subtraction. Now I'm done with 128, so I keep going. 64, actually, I'm sorry. When I do this subtraction, I'm going to just mark down with a 1 which number I subtracted. Next up, 64 exceeds 39, so I just cross it out. 32 is less than 39, so I'm going to go ahead and subtract that. The nice thing about this technique is if you ever mess up and you accidentally subtract a number you shouldn't have, you'll get something that's negative, and then you know you've messed up. You should always stay in positive numbers here. Okay, so we're done with 32. I'm going to write a little mark to say that I subtracted that one. Keep going. 16 exceeds 7, so I just cross it off. 8 exceeds 7, I just cross it off. 4 is the next value, so I'm going to go ahead and subtract that off. Cross it out, mark it that I subtracted it. 2 also works, so I'm going to go ahead and subtract 2 out of here to get 1. Mark it off to show that it has been subtracted. And then finally, 1 also works. So I'm going to subtract 1 off here to get 0. Cross it off and mark to say that I subtracted it. Once you get to 0 down here, you stop and you fill in all of the gaps on this right-hand side with zeros. So everywhere where I did not make a mark just becomes a 0. And now I'm actually done. I just read this column of numbers from the bottom going up, and that is my binary representation. So here I would have 0, 1, 0, 1, 0, 0, 1, 1. Again, just doing this column of numbers bottom to top. And just like in the decimal world, we often just omit any leading zeros. So I'm just going to remove that. It doesn't change the value of the number. And that's it. This is the binary representation of what we started with, 167. Okay, so the last thing we're going to look at is binary addition. So to motivate this, I'm also going to start off with an example in the decimal world. So say we want to take 147 maybe from before, and we'll add that to, I don't know, 62. Say. Now, you can probably just do this in your head, but if we remember back to whatever grade we learned how to do longhand addition, you do this in columns. You start from the right-hand column, and we take just 7 plus 2 is 9. Next column, 4 plus 6 is 10. We can't write 10 as a single digit. So instead what we do is we write just the last digit of 10 here, and then we carry the 1 up here. Then after that's done, we do our final column, which is 1 plus 1 is 2. Oops. 1 plus 1 is 2. And so binary addition actually works in very much the same way. The only thing you have to get used to is that the numbers you're allowed to put down here are only 1s and 0s. So let's do a quick example for ourselves here. Let's see. Maybe we'll do this. Okay, so say I'm asked to add these two binary numbers. We do it in the exact same way as decimal addition. Start off with the right-hand column, take 1 plus 0, you get 1. Second column, again, 0 plus 1 gives us 1. Third column, 1 plus 1 gives us 2. Now, unlike in decimal, we cannot just write a 2 there. We actually have to break this up. In decimal, or sorry, in binary, 2 is written as 1, 0. You can take a second to think about this. And so then we follow the same pattern that we did for decimal. We write the last digit down here, and then we write this digit as a carry up there. Now, I'll go ahead and add this column here. And again, we get 1 plus 1 is 2. We can't write 2 there. So instead, we're going to write the last digit of 2 plus a carry. And then same deal again. This column, we get 1 plus 1 is 2. So I'm just going to finish this off by putting the the binary representation of 2 as our sum. So a couple key things to point out here. The summing works the exact same way as in decimal, as do the carries. The only difference is that you're only allowed to put 0s and 1s down here, and things like 2, or if we had gotten a 3, you'd have to write them in binary, and then you'd have a carry for your next column. Okay, so that brings us to the end of the binary section. Why don't we go ahead and open up the chat for just a minute or so and see if anybody has questions so far. I'm not seeing any questions come through. Is that because no one has questions? Or can I just not see it? Somebody texted me, says it's private. Oh, okay, now I'm starting to get people. Yeah, I guess people are messaging me privately. That also works. Yes, I can see this to the 2 people who just sent me that. Okay, so one person asked to please explain breaking up 2 and 3 into 1, 0 and 1, 1. So I can absolutely go ahead and talk about that. So these are basically just simple binary to decimal conversions. So if I asked you, or sorry, decimal to binary conversions, these are a little bit weird examples because they're so small. But if I asked you as just a question on a homework or something to convert the decimal number 2 to binary, if you followed my sort of approach from before, I guess, you would start writing down the powers of 2. So we would go 1, 2, and we keep doubling until we hit something that exceeds the value 2, which here is 4. I cross that out and I go to the previous value. 2 does not exceed 2, so we write it down. We subtract them off, we get 0. I make a mark here to show that I subtracted 2. And here we've actually hit 0 early, so I'm just going to stop and fill in every other thing here with a 0. Read this off from the bottom to the top. I get 0, 1, 0. Leading 0 doesn't matter. Cross that off. And this is how we get 1, 0 in binary. And for 3, you can do a similar idea. I would encourage you to do that as an exercise just to see how that works. Okay, let's see. So in binary addition, the only form of numbers is 0, 1, and in the chance it is 2, just convert it to 10. Or sorry, to 1, 0. Yeah, exactly. So if you have a column in your binary addition that looks like this, you would convert that to 1, 0 with a carry on the next column. And if you happen to have a carry with a 1 and a 1, then you get 3. And so what you would do in this case is you'd have a 1 as the sum, and then you would also have a carry. Okay. In the homework problems, it asked to convert numbers with a small 2 at the end of the number at the bottom. Does that mean anything, or is it just a symbol for binary? Yeah, great question. Sometimes when we talk about numbers with different bases, we write the base as a subscript at the end of the number. So for example, if I just write 100, how do you know whether this is 100 or 100 in binary? The way that we distinguish this is if I mean it as a binary number, technically I should write a little 2 right at the end. Okay, I'll take one more question here so we can shut off the chat. In binary addition, if you had a sum of larger than 3, how would you carry? The answer is you should never get a sum larger than 3. So for example, in this column right here, this is pretty much the worst case you can ever get. If you have 2 1s plus a carry, that's the highest you can go. There's no other place where you could get more 1s in this sum. Okay, so we'll keep going on to logic gates. Now, as I said right at the beginning of this presentation, binary numbers are sort of the very basic language that computers talk in. So just like before you start doing any math, you clearly have to know what numbers are and how to read numbers. We've talked a little bit about how to read binary numbers, which are the computer's representation of numbers. So now we're going to talk about sort of the next layer on top of that, which is how we start doing interesting things with binary numbers. So the way to think about these logic gates is essentially as like the elementary building blocks of computers. They're sort of the smallest, most elementary part of a computer that does some useful function. Then a whole bunch of these things get strung together to do everything from calculations to Zoom calls to Word documents and everything else you know on computers. It might not be obvious how that happens from the start, but that's just because these are such elementary parts of the computer. So the way to think about logic gates is they are essentially just a box that takes 2 inputs and spits out some other output. Now, again, I'm just going to do sort of a analogy, I guess, in the decimal world. You might have a box that you call multiplication. And this box takes 2 inputs. Say I call them, I don't know, 2 and 3. And then in this case, we can all tell that 2 times 3 should output 6. That's pretty much how these logic gates work. Now, I want to ask you, though, sort of like a thought question. If, I don't know, some alien race or something came down to Earth and had no idea what multiplication was, how would you describe this box? How would you get that information across to them? Well, one way you could think about doing this is by making a table. You could make a table where you list out every possible combination of inputs and what the black box does to get the output. So in this case, I would just start off with 1 maybe. So we know that 1 times 1 is going to be 1. 1 times 2 is going to be 2. 1 times 3 is going to be 3, and so on. And eventually down here, I'll get to 2 times 1 gives me 2. 2 times 2 gives me 4. 2 times 3 gives me 6. and so on and so on. So you can imagine that, I mean, this table, even if we only go from 1 to 9 in each of the columns, it's going to be a really long table, right? And in fact, this is sort of just another way of looking at what you probably know as a times table, which is actually the way that we learn multiplication in the first place. It turns out that defining logic gates for computers in the binary world works exactly like this. Again, the only difference is that instead of using all the numbers 1 to 9, we're only going to use 0 and 1. Here's an example of what that might look like. Notice that this table is way shorter than the one that I just drew in part. And the reason is that each input can only be 0 or 1. And so every possible combination of zeros and ones in the input only actually requires these 4 rows. That covers everything that could be plugged into a logic gate. In the output column, we just list out what binary number this gate will output at the end of the computation. So let's go ahead and look at some concrete examples of this. First up, we have the NOT gate. So the NOT gate is actually the only gate we'll see for now that has only a single input, which is a little bit different than the diagram I just showed. And the way we denote it is if A is our input, not A, we draw with this little bar over top, is the output. As I just mentioned, the way we define a logic gate is with a truth table. In this case, we only have one input, so it's a really, really simple truth table. You can either have 0 or 1 as your input, and then the output is just going to be flipped. So a 0 becomes a 1 becomes a 0. We say that we flip the input to get the output. Now, as sort of a memory trick here, I guess, a lot of times when we talk about binary, you'll hear people talk about it not within the context of 0 and 1, but actually within the context of false and true. And so the way to think about the NOT gate, the reason it has this name, is quite literally because you can think of, not false. Well, what is not false? Something that's not false is true. And then equivalently, if something is not true, then it must be false. And so that's how this gate gets its name. Whenever we draw circuit diagrams, we would draw the NOT gate looking like this. And the way to sort of remember this internally, I guess, yeah, it's a triangle, but the point to really look at here is that we have this little circle at the end. You'll notice as we get to other logic gates in the future, this little circle denotes a NOT gate. So we'll just keep that in mind, but this is what a NOT gate looks like on its own. Next up, we have an AND gate. So this one, just like the more generic example I gave at the beginning, takes 2 inputs, A and B. And then we use this dot here to represent the AND gate. Now, the dot is intentionally reminiscent of multiplication because if you look at the truth table, it kind of just looks like what you would get if you multiplied the 2 inputs, right? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And it's not until you get to the last row that 1 times 1 gives you 1. If you prefer to think in this sort of true-false analogy that I brought up before, you can literally, again, just plug in the word and. So if we have sort of, I'll start off with like false and false. If we have false and false, the whole thing evaluates to false. Even if one of these is true, we can't say that both A and B are true, so the whole thing is false. It's only if both A and B, hence the gate's name, are true that you output true. Okay, so what does this gate look like in circuit notation? It looks like this, basically like a big capital D kind of thing. That represents an AND gate. Now, these circuit drawings, by the way, I don't really have any good memory tricks for them. I think this is kind of one of those things that you just need to memorize what they look like. Next up is the NAND gate, which is heavily related to the AND gate. In fact, as you can tell from the sort of algebraic expression up here, it is literally just an AND gate, then with the entire thing knotted. So remember, this bar over top is the symbol we had for the NOT gate earlier on. Looking at the truth table, you'll notice that, again, this looks pretty similar to the AND gate. The only row that's different is the last row. The difference here is that instead of 0, 0, 0, 1, as we had for AND, now we have 1, 1, 1, 0. Now, for these sort of composite gates, right, this is an and a NOT put together, sometimes what I like to do is I will draw myself sort of an intermediate column in the truth table here, and we'll just call that column A and B. And then I'll just fill this in from the previous slide. So it was 0, 0, 0, 1. Now, note, to get the NAND gate output, all you need to do is flip all of these. So you apply the NOT gate to all of these, and then you get your result. The circuit representation looks like this. So again, it's the capital D sort of shape that we saw for the AND gate. The difference now is that we have a circle at the end. Remember, before I said the circle is associated with the NOT gate. And so this gate is literally equivalent to an AND gate followed by a NOT gate. It is exactly the same thing. We basically just shorten this whole thing by putting the circle on the end of the AND gate. Next up is the OR gate, so this one we denote by this vertical bar in the middle of our two operands. The truth table for the OR gate looks something like this. And so again, if you think of the sort of true-false analogy that I had before, the way to think about this is A or B true, right? So in this row, A and B are both false, so the whole thing is not true. But in every other row, either A or B or both is true, and so the output is true. This is what the circuit diagram looks like. So it looks kind of similar to the AND gate. Again, I think you just kind of have to memorize what these look like. What distinguishes the OR gate is this kind of curved backing on it. So even in your own notes, try to be careful with how you draw these things. Next up, we have the NOR gate, which is very similar idea to the NAND gate. So I'll go through it fairly quickly. The truth table looks like this, which is again, looks very similar to the previous table, except that all of the bits are flipped. The circuit representation looks like this. So again, standard OR gate with a little circle at the end is perfectly equivalent to an OR gate, literally followed by a NOT gate. The last one we're going to talk about here is the XOR gate, which is a little bit of a unique one, I guess. What XOR actually stands for is exclusive OR. Now, I've always found this name kind of unhelpful. It does include the word OR, and as we'll see in a second, this gate is kind of similar to the OR gate. But the meaning of exclusive is kind of not immediately apparent. So I think for this one, you just kind of memorize what it does. Here's the truth table. Earlier, I said that this gate is sort of similar to the OR gate. And the reason is that if you look at the first 3 rows of this table, these are the exact same as OR, right? 0 or 0, so false or false, neither of them are true. The whole thing is false. Here, A or B is going to be true, so we get true. The only difference is in this last row. When A and B are both true, then the XOR gate outputs false. Here's how we draw it. Again, as I said before, it's similar to the OR gate. So you start off with this familiar OR gate structure with the curved back on it. The only difference now is we put a second curved back on it. So it's got this kind of double line toward the back. That's how you indicate an XOR gate. Okay, so I will pause and we'll open up the chat again for any questions that you have about the content so far. Okay, so some really quick questions. Is the if statement or any other statement a large part of quantum computing? If you're not familiar with this, definitely don't worry. The short answer is no. The most important thing for quantum computing is these logic gates, which is why we're going over them here. Where do we find the homework? Ask that on Discord. That is more of like a logistics question. Can there be more than 2 inputs for any of the logic gates? Yes, absolutely. So sometimes you will have a logic gate that has, for example, 3 inputs. So you might have A, B, and C. And the only thing that changes here is the truth table. The truth table is going to be longer because you still have to write out every possible combination of those 3 bits. So they could all be zeros. They could be like this. They could be like this. And this is one of those things where you can just look at it, convince yourself that there is no combination of the inputs here that I've missed. And some of you might even notice that all I've done here is I've counted up in binary. So this first row, 0, 0, 0 is 0 in binary, 1, 2, 3, 4, 5, 6, 7. So that's one sort of trick you can use to generate these tables, is to just count up in binary. Could I go over what the, okay, so a couple of people are asking about the NOR gate. I will definitely go back to that. So in order to understand the NOR gate, you first have to understand OR. So I'll do a very quick recap of OR. So the thing with all of these logic gates, to some extent, you just have to memorize what the truth table looks like. And so for this one, what you can memorize is that only the row with 2 zeros as the input will be 0. Every other row has 1 as the output. If you liked the sort of true-false analogy that we had before, you can think of this as asking, is A or B true? If A or B is true, then you're going to get a 1 in your truth table. Otherwise, you get a 0 in your truth table. Now, that's how the OR gate works. What about the NOR gate? The NOR gate is very similar idea, except that all of the bits in this last column are flipped. So like I said with the AND gate, one thing I sometimes like to do with these problems is go ahead and draw myself sort of an intermediate column here, A or B. So I've just removed the not. And then I fill in exactly what we had on the previous slide, which is 0, 1, 1, 1. To get the NOR gate, I just go ahead and flip all of these bits. And that gives me NOR. Okay, so we'll close off questions. I had one person say the logic for duplicating bits. We won't go over that right now, but you can definitely work this out on your own. It's something you can do with what you've learned so far. Why is it needed to make a picture of these logic gates? Is it important to remember what they look like? That's a good question. I guess this is just these circuit diagrams are a representation you will see in the real world. And you'll see that it becomes particularly important for quantum computing, is all I'll say. So you're totally right that they're basically just equivalent in the classical computing world. But you'll see that these diagrams are quite important once we get to quantum computing. Okay, so with that being said, we've hit the end of our lab time. We'll do another really quick Zoom poll. So same question as before. On a scale of 1 to 5, how do you feel about your understanding of this week's content? So go ahead, give that a rating in the Zoom poll, and I'll wait just a few seconds here for everyone to cast their votes. Okay, it looks like most people have actually already voted. Good, looks like there's generally an improvement. So that's always good to see. Okay, so we have just a couple of minutes left. I will do one piece of the optional content. So for this, we're going to look at the 1-bit adder. I'm going to read out this problem statement, and then I'm just going to talk a little bit about how you might approach this. We're not going to have time to work through the full solution, but I hope with the setup I give you, you would be able to do it on your own. So the question is, design a logic circuit to compute the sum of two 1-bit binary numbers. Have one output, sigma, so this letter right here is pronounced sigma, to represent the sum, and another output C for the carry. Now, the way to approach these problems, so I guess let me take a step back. This problem is giving you an English description of what your circuit should do. Whenever you get an English description of what your circuit should do, the first step is to convert it to a truth table, always. So I'm going to go ahead and write myself a truth table here. Input 1, input 2. And now my two outputs are already labeled for me. They're sigma and C. So again, how did I get that information? Just read it from the question. We're asked, the input is two 1-bit binary numbers. We have one output called sigma and one output called C, the carry. Now, just like any 2-input logic gate, I'm going to write all possible combinations of these inputs. And now I'm going to try and look at what the sigma and carry columns should be. It's now my job to fill in this truth table based on the English description. So instead of having a logic gate, this time we're going to fill these things in based on the English description. So if I sum 0 and 0, think about the binary addition slide that we had before. If I sum these, I just get 0. And I do not have any carry because I didn't go up to 2 or 3. You keep working this out. So my next example, I would try adding 0 and 1. You know, what would I get here? Would I have a carry? Repeat that for every row of this table, and you'll get a bunch of values here to complete your truth table. The last step, once you've completed your truth table, is to look at these last two columns and try to figure out if any of the truth tables we've seen before, if any of their outputs match these last two columns. Those logic gates will give you the outputs that you need. So again, you fill out your truth table, you complete these last two columns, and then you look back at all of the logic gates you know and what their truth tables are, and you basically just try to match them. You try to find one that matches the output columns you've written down. All right, so I believe that's all the time we have for today. We'll try and wrap up right on time. But thank you all so much for coming out to the first lab. I hope that this was helpful to grasp some of this week's content. Again, if you have leftover questions, if it's on the optional stuff, this 1-bit adder, don't worry too much about it. But definitely, if you have any questions about the lab material, feel free to ask it on Piazza, and we will do our best to get to those questions. Thank you again for coming out, and have yourselves a good night.